Hello and welcome to Mechanical Y. Here I have two pitchers. Each is filled with some water and some ice. This pitcher clearly has more ice in it than the other. So which one is colder? Some of you will be inclined to say that the pitcher with more ice is colder. But this is not the case. As it turns out, both of these are actually at the same temperature. So let's prove it. If we take this cooking thermometer and plunge it into the water of 1, we see a temperature of about 1 degree Celsius. Warming the thermometer up a bit in my hand to show a response, we can then plunge the probe into the second pitcher, and we see it too has a temperature very near 1 degree Celsius. And no, there are no tricks here. They both have ordinary tap water and ordinary ice. So why are they the same temperature if one has more ice? Intuition tells us that more ice means more cold, right? Well, not quite. The first key to understanding this is to realize that both have water and ice in them. Secondly, we must know that we have allowed these two to come to equilibrium internally. The system must be at or very close to a state of rest, also known as a steady state. We can't just take boiling water and dump a heap of ice in it and start taking measurements. Both of these pitchers were filled with water and ice and then allowed to sit for a time. Thirdly, we must understand conservation of energy. Both of these are sitting at rest on a table under the same conditions, and neither is generating energy as far as we can measure here, though a very small amount of energy is being transferred in from the surroundings. But this heat transfer rate is slow enough that will not affect this experiment. The internal energy transfers of each individual system are now more easily understood. Liquid water needs to lose energy to freeze. So when a drop of liquid water comes in contact with ice, it loses a little bit of energy and freezes. But where does that energy go? Energy must be conserved and energy must go somewhere. That energy is absorbed into the ice, which now has just a little bit more energy and just enough to melt that small amount of ice. In fact, the amount of water that freezes into new ice in this situation is the same amount that melts out of the original ice. It has to, according to the law of conservation of energy. Letting the system rest means that the ice slowly warms up to just about its melting point, and the water cools to just about its freezing point, until they are about equal, and any further cooling and freezing of water causes the ice to melt, and vice versa. The temperature is always going to be at about this transition point, where the liquid freezes or solid melts, so long as the two are present in a steady state. This experiment isn't the most isolated or perfect condition, so these two come to rest at just about 1 degree Celsius. However, it is important to note that there is a difference between temperature and total energy. Yes, these two are at the same temperature, but the one with more ice in it does in fact actually have less energy. And this has to do with the ice being slightly less dense than water, therefore making this pitcher have a slightly lower mass of water than this pitcher. So if they are at the same temperature, but this pitcher has slightly less mass, it means that this pitcher actually has less energy. Nevertheless, the phenomenon of equalizing temperatures is also present with gases in equilibrium with some liquid. If I had a container with both steam and liquid water in it, the temperature would be about that where liquid evaporates or water vapor condenses, regardless of the amount of steam, as long as there is some liquid water in the vessel. In these conditions, this would be just under 100 degrees Celsius. This property is especially useful in cooking. Even without a thermometer, we can establish consistent temperatures. That is why so many recipes call for boiling water or ice baths. And I can even use this knowledge to calibrate thermometers or other measuring devices. Just make sure that atmospheric pressure is considered, as that affects the point at which this transition occurs. It is important to note that ice alone without any liquid can be cooled to below its freezing temperature. Similarly, steam alone without any liquid can be heated above its boiling temperature. In extreme cases, we can have liquid water below its freezing point by not allowing ice crystals to form in what is called a subcooled liquid. Similarly, we can have liquid water above its boiling point by preventing bubbles from forming, which is then called a superheated liquid. But these two latter cases are unstable and need more carefully controlled conditions to be formed and maintained, and they can even be dangerous if they occur. There's also one more special case that can happen. We can have ice, liquid water, and steam all at the same time. This is a very special point called the triple point. Anytime a little bit of ice melts into liquid, a little bit of liquid freezes. And anytime a little bit of steam condenses, a little bit of water evaporates. For water, this condition occurs at about 0.01 degrees Celsius at a pressure of about 611.2 pascals, or about 0.6% the pressure currently in this room. Both temperature and pressure need to be just right to get this special condition, so it is somewhat difficult to achieve a triple point without specialized equipment. Nevertheless, I hope you found this interesting, and I hope you share and like this video. And also, please visit us at our website, www.mechanical-y.com.